Continuing with our project setup, one thing I didn't show you is in the weld joint window, we select a path and you can compute welding times. Based on the welding procedure, you have the velocities saved there and the length of the weld path and the start and end that you put here. You can compute welding times. We see here it's approximately 10 seconds for our weld path and the weld procedure that we have given. It's necessary to do that computation at this point. Okay, and now we will set up some boundary conditions. In our boundary condition for thermal, we have nothing really to set up here, but we could set up convection boundary conditions, Dirichlet, flux, laser flux. There are some defaults set up here for global convection coefficients and ambient temperature, contact conductance. It's all the defaults. You can edit those and change them if you wish. Set up boundary conditions stress. Now this is where we enter this file that we save for the fixities that we pick the nodes on. We set here an end time. I've given it 1 hour. You can put whatever you want here. We have 10 seconds of welding and then it cools for an hour. This is more than enough. It's important to apply these separately in order for it to take hold. Otherwise you can edit these things and wonder what happened. It didn't take effect. You need to apply. We don't have any pressure BCs or nodal forces to worry about in this project. So we will leave that window. And now we have the process parameter window where we can set various parameters for thermal, microstructure, and stress. We'll ignore the other ones for the time being. For thermal, we have a number of parameters here, but again, only a few of them usually need to be changed. The main one is the analysis in time, which you can edit. The power model, sometimes we use Dirichlet temperatures instead of the power density. There's solver types. The more interesting, normally when we're doing the welding, if you don't set anything here, it does 2 time steps in the weld pool, which is set here. So it steps along half the weld pool size each time step. If you set it with used filler metal slices added per time step, it does 1 element slice per time step, which is a little more interesting visually. For the half the weld pool, sometimes depending on the size of your weld pool, it can be several elements each time step. This one is a little more intuitive to me anyway. That's the only change I'm going to make here. We have melting temperatures and stuff that can be edited here. There's actually quite a number of things, but most of them are special case. Okay, I'll save that. Set up process parameters microstructure. There's usually not much to change here unless you're doing something special. One thing I'll mention here is that the project, you can run thermal, microstructure, stress all in the one project, or you can split the projects into separate projects that can run simultaneously. You can then use this to select where the thermal data comes from in the data flow. The microstructure gets its input from the thermal project. In this case, we have a very small project, so I'm going to run them all in the same project. So the thermal data is coming from this project. Similarly, the process parameters stress. A number of parameters again, but a number of solver types. You again set the thermal to this, the microstructure to this, and we're using multi-frontal. There are a number, we could just use plain frontal if it's a very small project like this, but I just want to show the multi-frontal. There's other SSCG or Gauss-Seidel, the different solvers that can be used. For now, we'll just accept the defaults for the rest, and we will check out our element subdomains here. The subdomains are chosen from each weld joint. We have a number of elements that we can use in a subdomain, and for example, if you set it to 500, we will, for each 500, it will group those into a subdomain, and the complement will take this larger number as the number of elements that can be in a subdomain. Subdomains are so that the solver can take these different groups of elements and solve them separately. It's mostly used for very large projects where you only have a limited amount of memory in your machine, and you would like to limit the amount of equations that are needed at any one time. So you break your project up into subdomains, and then later it can be put back together by the multi-frontal solver. I only used the multi-frontal solver here to demonstrate the subdomain capability. Now I will continue in the next video showing how to actually solve this.